Welcome to The Explainer. Today, we're slicing right through the tech hype to answer a really fascinating question. Why doesn't the most advanced AI always win when it comes to predicting our energy grids? With data centers popping up everywhere and our digital energy demands absolutely skyrocketing, the pressure to accurately forecast our power usage has literally never been higher. We are constantly told that deep learning AI is this ultimate, magical silver bullet for basically every single data problem on the planet. But when it comes to actually keeping the lights on, managing millions of megawatts across a highly volatile national grid, is that actually true? Does throwing the most complex neural network at the problem automatically equal a more reliable power grid? Well, the answer might actually surprise you. Take a look at this warning shot from a recent study published in Science Advances. Researchers there prove that when unprecedented extreme weather hits, and we're talking about those exact record-shattering events that stress our grids the absolute most, traditional old-school physics-based models actually outperform state-of-the-art AI. No way, right? That is a massive paradigm shift from the usual tech narrative we're used to hearing. So to understand exactly why the latest tech falters here, we have to look at the core tension in energy forecasting. It's a framework we like to call the trade-off triangle. Basically, any grid operator or digital energy engineer is constantly locked in this intense balancing act between three absolutely crucial things: pure predictive accuracy, the interpretability of the model's decisions, and baseline reliability when, the weather conditions just get totally chaotic. Because at the end of the day, forecasting is ultimately about predicting this red line as accurately as possible. We've got our historical observations in blue, and we need to project exactly what happens next. But here's the thing. To know if a complex, super expensive AI is actually adding real value to that red prediction line, we first need a reality check. We really can't just deploy AI blindly and hope for the best. And that reality check, that's what we call our baseline. A baseline is just a simple, traditional statistical model, something like a REMA or a seasonal persistence model. These models basically assume that future demand is just going to follow historical, linear patterns. They're incredibly straightforward. Basically, if yesterday's power load was at a certain level and today is a pretty similar Tuesday, well, the load will probably be that exact same level again. Simple, right? It is the fundamental benchmark we use to judge absolutely everything else. Now, to measure how much better an advanced AI actually is compared to that simple baseline, we try to avoid using big, abstract megawatt numbers. Instead, we use a key performance indicator called MAPE. That stands for mean absolute percentage error. It's a really simple concept. It just tells us the average percentage difference between what the forecast predicted and what actually happened in reality. So a lower MAPE simply means a much more accurate forecast. And when we actually apply MAPE to the real world, well, the undeniable appeal of AI becomes crystal clear. Researchers ran some tests on the highly complex PJM hourly energy dataset. The traditional ARIMA baseline sat at around an 8.2% error rate. But get this, a deep learning transformer model completely crushed it, achieving a tiny 3.8% error rate. In the energy market, having your forecast error like that translates to millions of dollars saved and vastly, vastly improved grid stability. So why do transformers perform so incredibly well? It's because they use what are called attention algorithms. You see, traditional models read data sequentially, kind of like reading a book, word by word. But transformers, they process entire data sequences simultaneously. It's literally like looking at the whole page all at once. And this allows them to perfectly capture the complex, non-linear habits of modern consumers. Like that sudden massive evening spike when an entire neighborhood decides to plug in their electric vehicles at the exact same time. Okay, so that brings us to a really crucial question. If the AI is essentially twice as accurate as our baseline model, why are grid operators, regulators, and policymakers hesitating to adopt it completely? Seriously, why not just hand the keys to the entire grid over to the transformer models tomorrow? Well, it all comes down to the second point on our trade-off triangle, interpretability. You see, advanced deep learning models are what we call black boxes. They give us these incredibly sharp predictions, but we can't see exactly how they arrived at them, which, as you can imagine, is incredibly frustrating for engineers. On the other hand, traditional models are glass boxes. They offer total 100% transparency into the mathematical logic behind every single prediction. And in highly regulated energy markets, transparency isn't just a nice to have. It's legally required. Just imagine an AI forecast triggers the startup of an expensive, highly polluting fossil fuel backup generator. Regulators are absolutely going to demand to know why. And this is exactly where explainable AI, or XAI, comes in. By using tools like Shape, engineers can basically reverse engineer the black box. It reveals exactly which input variables influence the AI the most, proving why a specific decision was made. It really bridges that gap between raw accuracy and human trust. But wait, there is another massive flaw holding AI back here. Because machine learning models only learn from historical training data, they fail spectacularly at predicting brand new, record-shattering weather events. Basically, if it hasn't happened before, the AI simply doesn't know what to do. Actually, studies show these models consistently underpredict the intensity of unprecedented heat waves, and they overpredict cold extremes. When the physical world changes in ways the database hasn't seen yet, the AI simply guesses wrong. And this is exactly why traditional models make a massive comeback during crises. While an AI is out there simply looking for past statistical correlations, a traditional physics-based model is actually calculating real atmospheric and thermodynamic equations. It relies on the fundamental laws of physics, not just a spreadsheet of past events. And that makes it infinitely more reliable when the climate decides to do something entirely unprecedented. So what this means is that pure, raw accuracy on a normal Tuesday just isn't enough. An incredibly accurate AI that fails completely as an opaque black box during a historic blizzard, yeah, that is a massive liability. As researchers are pointing out, the real future lies in hybrid models. It's about combining the transparent, physics-based reliability of statistical approaches with the sharp, non-linear predictive power of machine learning. The best of both worlds, right? Okay, so how do we actually navigate all this? Well, here is our 5-point action checklist for the modern energy grid. Number 1, always establish a simple baseline model first. 2, rigorously track your MAPE to prove that the AI is actually adding real value. 3, prioritize interpretability by using explainable AI. 4, always rely on those physics-based models for unprecedented weather extremes. And 5, embrace hybrid systems that combine the transparent reliability of physics with the sheer predictive power of machine learning. So, what you should really take away from this explainer is that in the complex digital energy transition we're going through, simple, transparent models still absolutely matter. AI is an incredibly powerful tool, for sure, but it is not a silver bullet. So, are you ready to look inside the black box of our digital future? Hit subscribe, leave a comment with your thoughts, and join our channel to keep exploring these crucial technological shifts right alongside us.